My name is Ben Levin. I lead enterprise labeling at Scale, including several of our teams focused on autonomy and working with the autonomy industry.
Hi, my name is Kate Park. I recently joined Scale as our Director of Product. Using this photo because very recently went accidentally viral on Twitter as Elon's Korean bodyguard during Tesla AI Day. I was previously at Tesla before joining Scale.
Great. So we'll talk about three things today. The first is just a quick introduction to Scale and our role in the autonomy industry. The second is how you can unlock data from the fleet, and in particular, production autonomy sensors from L2, L3 vehicles. And third, using a fleet to really power each phase of a data engine. So we'll start off with just introducing Scale. Scale is really works across the autonomy industry. As you can see, we work with large OEMs like GM and Toyota. We work with tier one suppliers to those OEMs like Mobileye and Luminar. And we also work with many of the L4, L5 robotaxi companies. Neuro and Motional are some of the examples here. This talk is really focused on the L2, L3 autonomy space, but we do think that there's relevant material here for really everyone trying to do autonomy at scale. So Scale was founded in 2016. We have more than 600 employees based in San Francisco with a global footprint. As you can see here, we're really in a privileged position to get to work with many people who are trying to lead new AI programs. And our mission is really to accelerate the deployment of those AI applications. So let's start with just making sense of production sensor data. And for this, I'll start with a little bit of history, right? So let's start off with where autonomy started. That was really the DARPA program and the DARPA Grand Challenges. And as you can see, the model there was to put many sensors on a car. And in particular, many of these programs ended up with a top-mounted 360-degree spinning LiDAR. And if you look at a modern autonomous vehicle stack for an L4, L5 robotaxi, it actually looks pretty similar. Those are very clear descendants. Next slide. And so for this, basically the whole industry decided on one paradigm, and that was the data frame. If you've worked with autonomous vehicle data, you've almost certainly seen something like this before. It's just capturing all the sensors, putting them in a fusion at a fixed interval, so 10 hertz is pretty typical, and then synchronizing them and applying ego motion compensation. And from this, if you have that top-mounted LiDAR, you actually get pretty clean data. And most of the L4, L5 autonomy industry still works on that basis if you're a robotaxi company. Next slide. Modern deployed autonomy is actually different. So if you're trying to get real vehicles into the field and you're not willing to pay $200,000 a vehicle, there are a few key differences. So let's go through them now. Next slide. So let's start with the sensors. L4, L5 robotaxis really all have that spinning multi-beam LiDAR, high-definition cameras, and radar. Fleet-deployed autonomy is a lot more heterogeneous. Some players like Tesla are really only using cameras in their fleet. Many others are using forward-facing MEMS LiDAR, fisheye and stereo cameras. Many use radar. There's actually a lot more different types of sensor setups. So next, let's talk about LiDAR scan patterns. Those L4, L5 robotaxis all have what you could treat as a single source of truth, which is the radial LiDAR scan. Modern fleet-deployed LiDARs actually just have very different scanning patterns. They might have a Lissajous pattern, they might be rasterized, they might be software controlled. You can't really predict it. The hardware itself is also very different. So all the L4, L5 robotaxi companies basically ended up working on a singular form factor. And that was a robotaxi that would cost $200,000. If you're a fleet and you're an OEM, the reality is you're going to have multiple target form factors, cars, vans, trucks, etc. You're going to have multiple different models and probably multiple hardware packages tied to different trim levels or different types of features. And so what that really all means is that the perception strategy itself ends up being different. In L4, L5 robotaxis, it's mostly early fusion, aggregating all sensors together. And fleet-deployed autonomy is usually multimodality or a late fusion approach. So why does this matter? Well, that traditional data labeling paradigm I mentioned with frames actually fails when you start adding up all these production sensors. So here, if I add a second sensor to this, you can see the data doesn't make any sense anymore. You have these like weird shadows on the right. And the reason for that is pretty simple. It's fundamentally that these two sensors are not synchronized. And in fact, with most scan patterns, they cannot be synchronized. It doesn't even make sense to think about them being synchronized so they hit every vehicle at the exact same time. So you really need a new approach. So let's go to the next slide and we'll see that approach. What we've worked on with many of our customers and partners here is something we call frameless labeling. And what that does is it does away with this whole paradigm of requiring data frames on a fixed rate. What you can see here is we're actually taking two different sensors and we simply create what we call an activation whenever a sensor encounters an object. So with this, you can really add any number of things. You could add a radar, you could add two different cameras with two different frame rates. Because we're doing all the data annotation in continuous time, you don't actually need to worry so much about synchronization of those sensors. You can work with whatever combinations are on your production fleets or whatever combinations are actually in your data collection fleets. And then from that, it's really easy to export that data into whatever perception stack you're working with. So we have customers who use this to do sensor-specific perception. We have customers who actually use this to just create more accurate early fusion. And in some cases, we have them do one model for LiDAR, another model for cameras. If you're capturing everything at a much higher level of precision, you can export whatever you want. So that's the key to actually unlocking that fleet data in many cases, is kind of trying to move beyond the frame-based paradigm and work with a flexible combination of sensors. I'll now hand it over to Kate, who will talk a little bit about once you've unlocked that data, what do you do with it? How do you use a data engine to get into production?
Great, thanks, Ben. Okay, so once your data is unlocked, you can now collect data from your vehicles, annotate it to high quality using an advanced tool like what Ben described with Frameless, and train your first model. However, with just a few labels, your model will heavily overfit on your training data. If we were to plot model performance on that y-axis, you would be very early in your model performance lifecycle. So how do you get from where you are, which is that red line, to where you want to be, which is more of the production quality that's required for an ADAS or self-driving system that goes to customers? The solution is the data engine. Let's first define the data engine. We define data engine as the process of improving neural networks or machine learning models via data, as opposed to changing the architecture and tuning that through research. This is a slide from Tesla's Autonomy Day back in 2019, when we first kind of presented this concept to the world. And it's been further proven to actually work. The reason why a data engine is so key is that it's deterministic in actually guaranteeing model improvements, and it can be faster when you don't know if, let's say, a research experiment will work out. So also showing a slide from AI Day, which was a presentation during my time at Tesla, and I want to zoom in to the graph on the right. With every increasing data set in dark blue, the actual model metrics in green go up and up and to the right. So this is just a demonstration that this data engine concept actually works to keep increasing your model performance. The final state of a world-class data engine is as complex as this. We're going to work our way up towards this diagram, but there's really two axes here. The first is that within each box, there's going to be 3 different phases of the data engine, which we'll walk through. And then second, there's 4 components, which are the 4 actual boxes going from labeling, model evaluation, data collection, and data set curation. So let's step through that. The 3 phases that we've often seen in industry are the base phase, which unlocks a first cut of model performance, then the improvement phase, which bumps it up even further, and finally the target phase, which will get you to achieve that production quality. And for each phase, once again, we'll walk through the 4 components. We'll give you an overview of the phase, the labeling workflow, curation method, and evaluation strategy. So let's start with that base phase. In the first phase of data engine lifecycle or model development, your first job is to find enough data to train a model that just doesn't overfit. You should be thinking on the order of 1 million videos mirroring your customer distribution to unlock that first step in your model metrics. When it comes to the actual labeling workflow, this is probably the most simple labeling workflow that you can imagine. You would, for example, upload an unannotated task, and your labeling provider, like Scale, will return it to you with the actual labels. When it comes to the tooling or the curation that you need to do to explore this initial phase of data, you'll want to have some sort of data management interface that allows you to explore the distribution of this first base phase. So here we're showing the ability to see different axes and, let's say, the distribution of different object classes. We see that trucks are much rarer than people or cars. We can drill into the trucks, see that there's 21,000 examples of that, further drill into nighttime trucks, and see that for that specific slice, there's only 5,000 examples. So this tool is a little bit more of a data explorer, and we haven't quite curated anything, but is pretty crucial to understanding what is in your base phase of what is in your base data set. When it comes to evaluating your model in this first phase of development, we're really doing the simplest thing, which is looking at generic model metrics like loss or accuracy. And the main thing here is just to know you have a lot more ways to go. So to recap just that base phase, we introduced the most simplest form of labeling. In evaluation, we saw that we have a long ways to go. In data collection, we wanted to mirror the customer distribution. And for dataset curation, we had a tool to explore and query our data. So now let's move on to the next step, which is the improvement phase. In the improvement phase, now you're no longer just collecting random examples from your customer distribution. You actually want to start collecting examples that are targeted to where your models fail. So this is the goal here is to improve general model metrics. So think, how are you going to collect videos where models actually have poor performance? The labeling workflow now looks a little bit more complex. Instead of just uploading an unannotated task and then getting that returned to you, you now have this extra step of, let's say, our labelers reviewing your model predictions. So in this flow, you as the customer will upload let's say an unannotated task, and the model predictions will review the quality of those predictions. If it's bad, we'll label it and return it to you. But if it's good, it doesn't even necessarily need to be added to your training data set. That would just bloat it since it's already an easy example. When it comes to curation, you can also think of some automated forms to find these tricky examples that your models will struggle with. Here, we're using a tool that allows us to sort all unlabeled data with predictions on them by a score like active learning score. Another example would be model confidence. By doing this, you start to see trends like, okay, our model currently struggles with large trucks or curvy roads, but we haven't yet quite targeted those cases. We're just doing a general catch-all to find all the unknown unknowns that our model might be weak at. Another example to see how to curate and use better tooling to support this improvement phase is to also use some kind of smart sampling strategy. So here we're going to show you the smart sample feature, which allows you to define, let's say, a target sample size. Let's say I want to find 10,000 examples and maybe do some fancy filtering on some basic metadata like time of day. And in this case, we're filtering for dawn dusk, but you might also change your mind and do targeted towards nighttime. And then finally, you can choose a sampling option, in this case, uniqueness. So once again, this is a way to actually make sure you're curating a data set targeted at model weaknesses, and then get that labeled. Now for evaluation, I want to start introducing the more fancier tools that we have in our toolkit to actually evaluate and start targeting the next things to solve in your model. So in this video, we're going to explore, we actually have a confusion matrix, so you can start seeing, hey, our model starts to struggle between buses and trucks. We might drill into it, visualize those examples, and we have further filters on the left that allows us to constrain the weaknesses based on, let's say, false positives, model confidence score, a particular metric like intersection over union. So at this point, we're really just getting a little bit more advanced, drilling into the types of failure modes and visualizing them. So for that improvement phase, what we just did is we introduced the more advanced labeling workflow of model verification in that ground truth labeling box. We also showed you the advanced workflows and evaluation. We started to capture model failures and potentially even put like manual manpower to find those model failures, or use some automated methods like smart sampling. So we've done base phase, improvement phase. Now let's do that target phase. In the target phase, you are now actually specifically going after scenario tests, or what we might call model unit tests. So think of something as specific as finding videos of tunnel exits to actually push your model performance to that very end production quality. When it comes to the labeling strategy, this can either be the simple workflow of just getting particular examples of tunnel exits or two people on the side of the road, if that's your specific unit test, and labeling them. Or you might start to see, and we've seen this in a lot of our workflows, that people start wanting to do targeted fixes. So let's say you found that your model is really struggling with people on the side of the road with some rare object. You might already have that labeled in your data set, and you want to just surgically update the instructions on how to label that rare object, and we'll just do a targeted fix there. So both this kind of generic labeling approach and targeted updates is very useful for the target phase. When it comes to curation, this is probably the hardest part of this third phase, which is how do you get specific examples of what you want? So here we're showing natural language search, which allows you to literally just search in English for tunnel exits or rainy highway merges. It can bubble up all the examples in your unlabeled data set that match that criteria, and then allows you to send it for labeling. Some unit tests will be especially difficult to curate for, and so for this, we'll actually want to build a mini data curator classifier on the fly. To plug one of Scale's tool, Nucleus has a feature called auto tag that actually supports this. So what we're showing here is the user is saying, hey, here are 3 examples of drops on windshield that I want to curate more of. Maybe the natural language wasn't quite sufficient to get more. So we're going to literally train a mini classifier on the fly and bubble up more examples like it. And so now you see that there's even more. You can further iterate that classifier by adding more positive examples of drops on windshield to your little data set that trains the curator classifier. For evaluation, we actually should make sure that we're testing our model on those scenario tests. So here we're showing an overview of various scenario tests that we've curated, whether it's edge cases on crosswalks, those drops on windshields before, and you'll want to make sure that you have some evaluation tool to make sure that your model is not just being measured on the generic test set and looking at, intersection over union, but actual performance on specific scenario tests. So here we're just exploring through different models, and when we drill in, we'll want to actually see particular performance on a scenario test. So here we've got our specific tests, and I'll just let the video play, but the point being is you want to make sure you have both qualitative, like looking with your eyes, and quantitative metrics to make sure you're improving. Awesome. So that target phase is now starting to complete the data engine picture. We've started to label edge cases. We're actually testing our model on scenario tests. We've collected those edge cases from our fleet or curated them with natural language or auto tag, which is on the fly model data classifiers. All of this was just to improve one model. So now you're at production quality, but you're going to have to repeat this for every single model for a self-driving or ADAS program. Think doing this for lanes, pedestrians, vehicles, traffic lights, you name it. And not just for every single signal or neural network on your car, but also making sure you have data distribution from your hardware platforms and sensor types. At this point, data is so key because yes, architecture research matters, but at the end of the day, you need to make sure your training data set has representation from all these different domains to actually get the performance you need. To that end, we've covered all the components and all the phases, but when you think about the amount of data flowing through these arrows, you want a bigger and bigger data source. So the bigger your data collection vehicle fleet, whether that's a particular survey like data collection fleet outrigged with particular sensors, or your actual production customer fleet in the hands of people you're selling to, unlocking data from them is key so that you can get as much data top of funnel, curate it as you will, label it, and then you can fuel this whole evaluation and data engine loop. So the key takeaways here are: one, as Ben described, your production fleet sensors are different from level 5 AV sensors, and your sensor data isn't quite ready to consume out of the box. Two, you'll want to use advanced labeling interfaces like 4D sensor fusion to label that sensor data at high quality. Three, there's several phases of the data engine to get your model to production quality. And four, you should create a data engine from your vehicle fleet as the foundation for an autonomous vehicle program. Thank you so much. We will open it up to questions, and I'll hand it over to Ben to ask the first question.
Sure. So the first question we got was from Jose Munoz, a project manager at Meta. And he asked, Kate, can you speak to Elon and Tesla's view on LiDAR versus cameras?
Yeah, so Tesla specifically was very vision focused, and the philosophy there was if humans can drive with their eyes, the goal was to get a car to drive the same. I think there's a lot of different approaches, and we see it's still an open problem, right? And so we'll see like how different sensors play here. But there's definitely like a vision only approach. We've also seen LiDARs and radars contribute to more redundancy to sensors. So it really kind of depends on what perception stack you want to take. Yeah, Ben, anything you want to add there?
No, I think that's right. And we were recently at a conference. The reality is no one quite knows exactly what it's going to take in the long run to power autonomy. You do still see a very strong scaling effect as LiDAR gets cheaper and cheaper. You also see some of these sensors even coming together. So for example, FMCW LiDAR blends a lot of the features you would traditionally expect in a radar together with the LiDAR. So I think what we will end up seeing is many people will take many approaches. Over time, the industry will standardize on a couple of things. But given that cars overall are not getting cheaper, but the sensors are getting cheaper, the trend is more and more sensors per car. And that's probably only going to continue accelerating.
Yeah, great. We have a question about frameless sensor fusion, Ben. So how does the new frameless sensor fusion approach you shared interact with mixed camera and LiDAR data? For example, can it accommodate a 10 hertz LiDAR, a 20 hertz camera, and a 15 hertz camera, which are not in sync?
Yeah, that's a good question. The short answer is that what's still very important in these systems is an accurate global clock. So if the sensors aren't in sync in the sense that you truly just don't know how one camera matches up against another, the solution really is at the hardware level. You need to basically run a wire from the camera into your global logger and make sure that you're getting a more accurate timestamp. The nice thing, though, about Frameless is that as long as you have that global clock, there are actually no requirements whatsoever in terms of the exact frame rate or configuration of different sensors. So we see customers even use this often if they want to experiment with adding a new sensor to their fleet. They don't want to have to synchronize it and do a lengthy integration process. They just want to see whether it will boost model performance. This approach will really let you just like add and subtract sensors as needed over time.
Great. Yeah, I see a question on, can you quantify the benefits of using the data engine approach? Definitely. So given that you have evaluation metrics, you can run an experiment by just adding a new data set. How much does that move the needle on those metrics? So what I usually recommend to people training models is try your architecture experiments plus data, but also do some experiments that only isolate the new data set as a change and see how much that improves your metrics. Once you get to kind of a plateauing trend, then it's time to kind of revisit your architecture, because in theory, any higher quality and bigger and better data set should continue to improve your model.
Great. There's another question for you, Kate.
Okay.
Someone's asking, they're looking at buying a fleet of Teslas to run as taxis before FSD starts. Does that mean that they need a data engine for their EVs? And will Tesla? Does that mean like Tesla won't have all the data necessarily for their locations? I think the broader question here is like, how do you think about scaling up the data engine as you shift operating domains and like go to new locations? How does that interact with the staged approach that you shared?
Yeah, so one of the domains we briefly touched on was, I guess, can be geographic domain. So at the end of the day, it's data, data, data. If you want to deploy your self-driving system or ADAS system, not just in California or Phoenix, Arizona, and you want to start expanding to Europe or Canada, you need some data distribution. You need data from those locations to make sure your model performs well. So we should use the same things that we talked about. We should create a scenario test for a particular country, get data for it, and make sure that it passes all the unit tests. If I'm looking at the question again, does that mean I need a data engine to train my EVs? In general, you should always have a data engine for any machine learning model development. So I'm going to say yes.
Yeah.
Great.
One more question. What can go wrong in the process of improving neural networks in the data engine? What are the mitigation best practices?
So I think what can go wrong is if at some point, it is possible that you won't see gains from your data because you're limited by the architecture. So I don't want to completely dismiss how that, model architecture is defined. And when I say architecture, I'm talking about, are you using a ResNet or a VGGNet or a transformer? So yeah, we should keep in mind that it is a dual effort between data and research to actually unlock model performance. Other things that can go wrong are just doing a whole data engine, and even just the labeling is extremely complex. So everything from managing the quality of your data sets, making sure your labelers are trained, having a really buttoned up taxonomy and instruction set, making sure that you have the operations to actually hit your throughput targets. There's so much blood, sweat, and tears when it comes to running these operations and building these tools. You really just want to make sure you're working with somebody who knows what they're doing or has all the resources to support like how complex this can be. Yeah, Ben, I wanted to ask you, what do you think has been the hardest challenges when running data projects?
Yeah, I think if you think about how this works, especially as more traditional automotive players start building out both data engines and more broadly self-driving stacks, the people who are approaching this in a very traditional waterfall way are ultimately going to be outperformed by those who can iterate quickly and change their models over time. So if you go back, 10, 15 years, the way to certify a new autonomous driving function was to build it, make sure it meets the requirements, drive it for 2 million miles, deploy it onto the car, and then never touch it again. And that's just not going to work when the consumer expectation is that you have a car that's getting smarter over time and that you can download new software to it through over-the-air updates. So as you think about moving from that waterfall once and done approach to a more continuous development process, things will go wrong. And the hard part normally is figuring out exactly what's gone wrong and making sure that it's still not creating a safety issue or not creating a bad driving experience. I would say the biggest key to that is actually some of the features that you demoed, Kate, around defining specific scenarios and continuously measuring performance on those scenarios. It is the wrong way to think about it of saying my model needs to go from 95% quality to 98% quality. That is going to get somebody killed. What you need is 100% quality whenever there's a safety critical issue. And you need to very clearly define what those safety critical cases are and be able to always monitor your performance against those areas. So I think that's actually the biggest challenge that people see. It's not just like what goes wrong wrong along the process. It's how do I set this up so that I have a continuous development and testing approach, as opposed to trying to just get it once, ship it onto the car, and never touch it again.
Yeah, that's a great point. Yeah, I think test sets can be so misleading sometimes, and those metrics. So if you don't actually break it up into almost human understandable subsets, then you could be hiding information. Let's say you have a model that improves by 1%, but when you drill into the ones that actually improved, they're all examples that aren't quite safety critical. And that's offset by, let's say, regressions in actually safety critical examples. So you really need to isolate every single scenario test. I see we have a question on kind of benchmarks and volumes of data. So the question is there a benchmark for how much data is needed at each stage of the data engine? It kind of depends per model, but in general, let's say the base phase is maybe like 1 million frames labeled. Your improvement phase can be like triple that volume, um, especially since the amount of data that comes out of the improvement phase, which is just the model failures, is some subset. So for example, let's say you are verifying the performance of your model predictions on 3 million images, and then only 1 million of those fail. Those million actually get added to the training data set on top of the 1 million of your base phase. And then for your target phase, generally think on the order of 10,000 to 100,000 per specific scenario unit test. But once again, this really varies based on the task or the signal that you're trying to train. So the more specific the signal, the less data is needed. I guess to make that concrete, like training a blinker signal would require less data than training a semantic segmentation generic model. Great. Any other questions here? I see.
I think there's one more around the improvement phase of the data engine and filtering for false positives. So is that automated or is that manually tagged by annotators?
I believe it is automated. Yes. And okay, here's another question. How much more effective is choosing data selected through the data engine rather than just labeling more data? So the diagram with the model performance plateauing, that is meant to illustrate that if you don't do any curation, your model metrics won't really improve the bigger and bigger your data set. So once again, this varies a lot, but I would think on the order of like 3x or 10x improvements if you actually curate the right data in terms of the model improvement compared to just random examples.
Yeah, and as you go into edge cases and long tail scenarios, that 10x go to 100x, right? Because if where your model is failing is, for example, emergency vehicles with their lights on, you might label 1 million frames of data and not label even one frame of an emergency vehicle with your lights on unless you have a data engine approach. So I think that's kind of the way you have to think about it, right? Is you hit a plateau on both general performance and then specific scenarios. Then over time, you think about more, how do I improve on specific scenarios? And that's when the data engine approach is almost the only way to do it in a cost-effective manner.
Awesome. Thank you so much for joining us. Yeah, we really enjoyed this. And please reach out. We also have our contact info. And please don't hesitate to email us if more questions arise.